Good morning children. We are on to the second video on the important questions of S block elements. One video I've already posted, so please see that first before you watch this one, and please watch the video till the end. The first question is the general configuration of group 2 elements. So the group 2 elements general configuration is NS2. Right. The second, it says that alkaline earth metals are denser than alkali metals. They are denser because of two main reasons. One, small size and better packing. Because they have small size, their packing will be more effective. Okay. And moreover, the density doesn't, vary uniformly down the group. It is seen that from beryllium to calcium, the density decreases. In the beginning, you find that it is decreasing from beryllium to calcium, and then from calcium to barium. From calcium to barium, the density is found to increase. Okay, the density decrease from beryllium to calcium is mainly because of decrease in the packing in their lattice. Okay, the packing becomes not effective from beryllium to calcium. That is why the density is decreasing from beryllium to calcium, and after that you find from calcium to barium density increases. Right? The next question says the second ionization enthalpy of the elements of group 1 are higher than those of group 2. So to answer that, you will write down for group 1 and group 2 what are their original configurations. They are NS1 and NS2. Right. After losing one electron, that means in +1 oxidation state, if you check, the group 1 elements will have noble gas configuration, and group 2 elements will have noble gas plus NS1 configuration. So now this will have very high ionization enthalpy. It's not possible to remove. That means the second ionization enthalpy for group 1 elements will be high because the second electron is to be removed from a noble gas. Whereas in group 2 elements, now if they lose one electron, they will acquire the nearest noble gas configuration, so they can lose it easily. Right? Next question says that compounds of alkaline earth metals are more extensively hydrated than alkali metals. Hydration enthalpy is inversely related to size. We know that alkaline earth metal ions are smaller in size, so their degree of hydration will be more. They get more extensively hydrated. Though if we only talk about alkaline earth metals, down the group their hydration enthalpy will decrease. So it is seen that calcium, magnesium, say magnesium chloride, it is associated with 6 water molecules. Calcium chloride is also associated with 6 water molecules. You do not have such hydrated salts for sodium chloride or potassium chloride. In that particular group only lithium forms, that is 2 water molecules it is having. Okay. Next, all alkaline earth metals except beryllium and magnesium impart color to the flame. Why they impart color? In alkali metals we've already discussed that. Okay, because their ionization energies are low. Even here in alkaline earth metals, you'll find all of them exhibit, but for these two. Because their size is small. Because the size is small. Due to small size, their ionization energy will be more. More energy will be required to excite the electrons. That is why they do not impart color to the flame. Rest all the elements you should be knowing their color also. Like you have calcium. Calcium is brick red color. It imparts brick red color to the flame. Then strontium. Strontium is crimson red color to the flame. And then you have barium. Barium is apple green color. Barium imparts apple green color. And the procedure how to perform the flame test is the same what I've discussed in alkali metals. Right. The next one says alkaline earth metals are weaker reducing agents than alkali metals. Even the answer for this is size. atomic size of alkaline earth metals is small. Due to small size, they will not be able to lose electron readily. That means their ionization enthalpy would be high. Ionization enthalpy is high, therefore the overall E0 value, the electrode potential value for alkaline earth metals is found to be less negative. It is found to be less negative. It is found to be less negative and more negative for alkali metals. And down the group, the reducing nature in alkaline earth metal will be increasing down the group, right? Then beryllium and magnesium are kinetically inert to oxygen and water. Because beryllium and magnesium have the tendency to form protective oxide layer. It forms a coating. It is both these elements have a tendency to form a protective oxide layer coating. Below 873 Kelvin. That means if you heat it, it might react, but below 873 Kelvin, they both form a protective oxide layer coating, which further prevents their reaction with the oxygen and water. Though if you are heating them, then they will react and form oxide and nitride like the other alkaline earth metals do, right? Then calcium, barium, strontium, they get attacked by air and water. As down the group, the ionization enthalpy decreases. If ionization enthalpy decreases, the reactivity will increase. The reactivity increases. Okay, so they will react with air. Let us write down, say, with respect to calcium. If we are writing, calcium will react with oxygen, calcium will react with the nitrogen present in the air, and it will form their corresponding oxides and nitrides will be formed. So they both react in air. Okay, and they can also react with water too. Like if they are reacting with water, they'll form their corresponding oxides, hydroxides. Next, they say that except beryllium, all other alkali metals are ionic in nature. Means their salts are ionic in nature. That is due to small size of beryllium ion. Beryllium ion is smaller in size, due to which, as per Fejan's rule, it will have more tendency to polarize the anion. So because of more polarizability, beryllium forms covalent halides. For example, we can have BeCl2. It is covalent. Whereas if you take any other halide, say magnesium, calcium, strontium, whatever, they are all ionic in nature. That's because of small size of the cation. It will have more polarizing ability. Right? Now beryllium exhibits abnormal behavior. So for this, the reason we can write down beryllium has small atomic radius, or even ionic radius is small in it. It has high ionization enthalpy and absence of d orbital. These are the three reasons why beryllium is abnormal. Okay, and it is having more properties like aluminium. Diagonal relationship it exhibits with aluminium. Beryllium cannot exhibit coordination number more than 4 is because of absence of d orbital. If you write down the configuration for beryllium, its valence configuration is just 2s2. So in the valence shell, it is having 2s orbital. At the same time, it is also having 2p orbital. So at the most, these 4 orbitals are available, wherein it can accept the electrons from the surrounding groups also. So maximum coordination number for beryllium can go up till 4. Whereas for the other elements like aluminium, it can go up till 6. That is because of presence of d orbital. Then the similar type of the question, both beryllium and aluminium chlorides have the bridged structures in vapor phase. In this case, suppose you write down their halides. Suppose we are writing, say, beryllium chloride, BeCl2, or you write down AlCl3. We find that both are electron deficient. These both are electron deficient halides. Their octet is not complete. Okay, you can just see beryllium has 2 valence electrons. 2 it is getting from chlorine. So it is having maximum 4 in the valence shell, and aluminium has 3 in the valence shell, and after that it is getting 3 from chlorine. So it is having 6 in the valence, and this is having 4. So their octet is not complete. So as to complete the octet, they are always found in the bridged structures in the vapor phase. So you can remember their structures. For beryllium chloride, it is Be here, 1 chlorine here, chlorine, 1 chlorine this side, here you have 1 chlorine, it is connected like this, you have 1 more chlorine, and from chlorine to beryllium there is a dative bond. Same way in this opposite side also you can find 1 dative bond, because chlorine has valence electrons present. Valence electron means the lone pair of the electrons present. One of it is involved in the bond formation this side, but the 3 pairs are there. They get coordinated with the central atom. So it tries to complete its octet. Right? So though in that also it's not complete, but still it will try to get more electrons. Same way AlCl3. AlCl3 also will have a similar tendency to exist as a bridged structure. Okay, like this. You'll have chlorine, chlorine. Okay, so you'll have like this. This chlorine giving electron here. This one also giving electron. So both aluminiums will get the electrons in their, valence shell. Then abnormal properties of beryllium. When you're writing abnormal properties of beryllium, one you can write down that it is hard, comparatively hard. It is having high melting point. Right? It forms covalent halides. It forms covalent compounds, in fact. Okay, you can even write down this one. The coordination number does not exceed 4. It is having the maximum coordination number of 4. Then beryllium does not react with air to greater extent because it is forming a protective coating. Okay, that is oxide coating you can write down. Okay, then you can also mention about that beryllium hydroxide or beryllium oxide. These are, amphoteric in nature. These are amphoteric in nature. So at least 4-5 properties beryllium you can remember which are abnormal. Right? Now we move on to the reactions. What happens when alkali metals react with water? You can take particular equation and write down, say alkali metal sodium. Sodium reaction with water. It will form the corresponding hydroxide plus liberate hydrogen gas. Okay, I am just writing the equations. You can balance them. Okay, so if you are balancing, actually you'll get 2 here and 2. With ethyl alcohol. See, ethyl alcohol, ethine, both even water. These are all proton donors. So these react with the alkali metal. Say I am writing with ethyl alcohol, C2H5OH. So what it will do? It will take this Na will take the place of this H, and H has to come out. So when you are writing the equation, it will be H2 this side, and you are getting C2H5ONa. That is sodium ethoxide is obtained. Sodium ethoxide will be obtained. So if you balance this equation, you will get 2 here for hydrogen. If not, what you can do is you can remove this and just put this as half. That's enough. Okay, you'll get sodium ethoxide plus hydrogen gas is liberated. Same way here, alkali metals, they react with ethine, which is also a proton donor, and it replaces the position of hydrogen. So you can have here Na, and hydrogen gas will be liberated. So if another side hydrogen also gets replaced by sodium, that is also possible. You will get both the sides substituted. Otherwise, it is only one. If we are writing, then it is called as monosodium acetylide. Monosodium acetylide. That is the product. Right? Alkali metals with air. If it is any alkali metal, then it would be reacting with oxygen and it will be forming the corresponding oxide. Okay, it will be forming the corresponding oxide. You can write down 2 here. If you're writing 2 here, means this has to be then half. right? So if it is the lithium, then it will form oxide plus nitride both. Okay, in this further, if you are using the higher alkali metals, then they may also form peroxides. If you use still potassium, rubidium, cesium, they may also form superoxide. But if general is asked, then only normal oxide it is going to form. Then with liquid ammonia, say sodium, it is reacting with X plus Y of ammonia, then it will result in the formation of ammoniated cation, say X amount of this is here, plus it will form ammoniated electron. It will form ammoniated electron, due to which it is having color, due to which it is paramagnetic. Okay. Then what happens when sodium peroxide Na2O2 reacts with water, right? So when this reacts with water, you can just write the equation Na2O2 plus water, it will form NaOH plus hydrogen peroxide. Okay, so when you are balancing it, you will get this here, right? If it is with peroxide asked, that is superoxide asked, say KO2, potassium superoxide, this is sodium peroxide, this is potassium superoxide. This with water, it will form the corresponding hydroxide plus, I think here it is hydrogen peroxide. Yeah, when we are using this peroxide, this will be forming peroxide only here. Okay, when it is superoxide, you will get hydrogen peroxide plus oxygen also. Right? So just make note of that. If it is peroxide here, you will be getting hydroxide plus peroxide only. Right? So you will have 2 here, 2 here and 2 here. Now it is balanced. Right? Now lithium carbonate is heated. When lithium carbonate is heated, you are getting this lithium carbonate. And when you heat it, what you will get is, you will be getting lithium oxide plus carbon dioxide. No other carbonate on heating will give carbon dioxide gas. It is only lithium carbonate which on heating will give this. Right? In the same question, suppose it was asked to you as what happens when sodium carbonate is heated, then nothing will happen. If it is heated, then nothing will happen. It will not decompose further. When lithium nitrate is heated, lithium nitrate is LiNO3. When you heat this, it will result in the formation of the corresponding oxide plus reddish brown gas plus oxygen gas. Okay, I'm just writing the equations. Balancing you can, I think, do on your own. Sodium nitrate. Sodium nitrate, when it is heated, say NaNO3. When it is heated, it results in the formation of sodium nitrite plus oxygen gas. It doesn't give reddish brown gas of NO2. So please make note of this. Alkaline earth metals with water, it will form its corresponding hydroxide plus hydrogen gas will be released. When it is alkaline earth metal with HCl, some acid, it will form the corresponding chloride plus hydrogen gas will be released. And if it is magnesium with liquid ammonia, then it will form a similar type of the compound as we did earlier with respect to this thing, alkali metal. Say this is X plus Y, again you will be writing ammonia. So this will be there and the charge over this will be 2 and 2 electrons will be given out. So you will write down this with ammonia with this Y and this will be -1. This is taken twice. Okay, when magnesium nitrate is heated, then what will be obtained? It is like lithium. It will form magnesium oxide plus reddish brown gas plus oxygen gas. Clear? Now suppose you are asked to arrange them in the increasing order of the covalent nature, then you will be applying Fajan's rule. You will apply Fajan's rule, which says smaller the size of cation. If the cation is smaller and anion is large. If anion is large, then it will be having more covalent behavior. So in this case, this is, central atom is same. When central atom is same, observe the anion. So I is the largest one. So largest anion. So LiF will be least covalent. Then you have LiCl and then LiBr, and the maximum will be LiI. Okay. Then you have covalent nature in case the anion part is constant and the cation is changing. The smallest cation will be maximum. So you will have LiCl, then you have is NaCl, then you have KCl, then RbCl, and the least would be cesium chloride. Clear? Now suppose you are asked for these fluorides thermal stability. Check for comparable size. If the size of cation and anion are comparable, then the bond form will be strong. So this is the smaller fluorine. Smaller size halogen. So it will form a stable compound with fluorine. So the order for the thermal stability will be, this is maximum, then you have Na. After that is NaF, and then you have Kf, RbF, rubidium fluoride, and the least is cesium fluoride. It can also be asked this way, that enthalpy of formation is becoming less negative down the group. Enthalpy of formation becoming less negative down the group, in a way we mean to say that the thermal stability is decreasing. The reverse is true for chloride, bromide, iodide. For all chloride, bromide, iodide, the thermal stability down the group is increasing, because chloride, bromide and iodide, they are larger anions. They will form stable compound with the larger cations. So in them it will be LiCl least, then you have sodium chloride, then you have potassium, rubidium and cesium. Last will be cesium, that is maximum will be cesium. So thermal stability for all chloride, bromide, iodide is becoming more negative down the group. The reverse was for fluorides. Melting point. Melting point is decreasing. In case we are talking about the fluoride, it is decreasing down the group. So maximum is fluoride, lithium, and then sodium fluoride, then you have potassium fluoride, then you have is rubidium, and the least is cesium fluoride. Right? Then we come to the stability and solubility of carbonates. For alkali metal carbonates and bicarbonates both, the stability and solubility increases down the group. Stability increases down the group. Same is for solubility also. Okay, it is increases down the group. Right? Suppose I take particular example of carbonate only I am taking. Right? Stability we are saying increasing down the group. That means lithium carbonate is least stable. Li2CO3 is least stable. That is why on heating it can decompose. Then you have sodium carbonate, then potassium carbonate, rubidium carbonate. Then you have the maximum stability is for cesium. The reason for this is the stability for carbonates and bicarbonates, because carbonate, bicarbonate are larger size anions, so they will form stable compound with a larger cation. Then solubility increases. The same order you will be writing for the solubility also. The same order will be written for the solubility. Reason for the solubility is the decrease in lattice enthalpy is more than the decrease in the hydration enthalpy down the group. So because lattice, and there are two factors only for the solubility. If the solubility will be more if hydration enthalpy is more, right? But if the lattice enthalpy decreases much more down the group, both are decreasing down the group, but the decrease in lattice is much more than the decrease in the hydration enthalpy. Therefore solubility is increasing down the group. And here it is also said that lithium hydrogen carbonate is not stable at all. This is not stable. It cannot exist in the solid state, whereas all others can exist. Okay, now we move on to the basic nature down the group. Basic nature of these hydroxide increases down the group. That means lithium hydroxide, then you have sodium hydroxide, then you have potassium hydroxide, rubidium hydroxide, and the maximum is cesium. Metallic nature is increasing down the group. That is the answer. Then if you are asked to arrange their solubility, thermal stability, basic character of the hydroxides of group 2, all are increasing down the group. They are all increasing down the group. Stability, basic character, solubility, all are increasing. Basic character is increasing because metallic character is increasing down the group. Solubility increases because same reason, both will decrease down the group, lattice and hydration enthalpy. Okay, both are decreasing down the group, but decrease in lattice is much more than. Decrease in lattice enthalpy is much more than decrease in hydration enthalpy. Right? Now, if you are asked to arrange for the solubility and stability of carbonates and bicarbonates, there are two different things, carbonate and bicarbonates. You will see that stability in both the cases, carbonate and bicarbonate, stability increases down the group. Reason being, larger anions will form the stable compound with a larger cation. Stability increases down the group. Whereas the solubility decreases down the group. Solubility decreases down the group. Why this decreases? The answer for that is hydration enthalpy decreases down the group. Hydration enthalpy down the group decreases. So because hydration enthalpy decreases, the solubility will decrease. Right? Then mention properties of beryllium similar to aluminium. You can make note of those properties which are similar, like both form protective oxide layer they are forming. Okay, then both are having those halides. The halides formed by them are Lewis acids. Their octet is incomplete. Okay. Both form covalent compounds. Okay. Then another one you can give is both form amphoteric oxides. Okay. You can even add that both are forming the chloro bridge like structure. Fine. Then if you are asked to draw the structure of this beryllium chloride, you will draw a similar type of structure which we have drawn, but in this case you will have more number of chlorine surrounding this. This will be the structure you will draw in the solid phase. Earlier which structure we had drawn, that was in the vapor phase. In the solid phase, this will be the structure. Okay, next, if you are asked to answer like beryllium hydroxide is amphoteric in nature, justify. So in this case, what you do is you will be writing equation. Beryllium hydroxide equation with acid, wherein it forms the salt plus water. At the same time, you can also write down its reaction with the base. With the base, say OH minus, and it forms a salt. It will form a salt. Right. So this shows, the first one is showing the basic nature because it is able to react with the acid. This shows the basic nature of beryllium hydroxide, and this one is showing the acidic nature because it is able to react with the base and form the salt. Okay. Beryllium is abnormal. This we have already done this. Beryllium is abnormal. Why beryllium is abnormal? Because of size, small size you can write down. You can write down ionization enthalpy is high. You can write down the absence of d orbital. Okay. Yeah, these two questions are repeated. Properties we have done, which are different from alkaline earth metals, will be similar to the beryllium. Okay, yes, so this one is repeated. In fact, this one is repeated. Beryllium, aluminium, we have already done the properties which are similar. So in what way you find that beryllium is different than the alkaline earth metals? You can mention all the properties where beryllium is similar with aluminium. They will be different with the alkaline earth metals. That means they form the covalent halides. Then they are forming amphoteric oxide. Then you can also mention about the coordination number does not exceed 4 and so on. Okay, that's all for today. So please learn these answers. Thank you.